Dear students, welcome to the lecture on the Lyapunov stability theory 2. So, in the previous lecture we have seen two theorems, one on the stability and another on the asymptotic stability. So, we have seen various conditions like positive definite function, the function of class K and decreasant function, etc. So, in this lecture initially we will see some examples of such functions, and then we will proceed with the theorem on the instability of a dynamical system. So, if we consider the function v of say x1 x2 equal to a x1 square plus b x2 square, where a is greater than 0, b is greater than 0. So, this is a positive definite function. So, it is very clear that v of 0 0 is 0 and it is always positive. Similarly, second example like v of x1 x2, if you say a x1 square plus say some b into 1 minus cos x2. So, if you consider this example, when x1 is 0 and x2 is 0, the value is 0, v of 0 0 is 0, and always the two values are positive. If a is greater than 0, b is greater than 0, it is also positive definite function, provided x2, for example, now if you consider this one v of say x1 x2, it is equal to simply a x1 square if a is positive. So, this is positive semi definite. Because v of 0 comma any x2 is also equal to 0. For non-zero points the function value is 0, and v of 0 0 is also equal to 0. So, it is positive semi definite function. Now, if you consider the we have seen that if v is positive definite, then it should be greater than or equal to phi of norm of x, where phi is the function of class K. So, we should show that for all these examples how to find this phi expression. So, for example, if v x1 x2 is some expression, let us say 3 x1 square plus half x2 square. So, it is obviously positive definite function, and we can also see that it is greater than or equal to half times x1 square plus x2 square. So, it is the function phi of norm of x, so which is equal to the phi of norm of x function, that is nothing but half, you can say r norm x square this x. So, this is the function. Similarly, for the function v x1 x2, which is equal to x1 square plus 1 minus cos x2. So, as we have seen, it is positive definite function in some neighborhood. So, how to find a function phi for this one? So, it can be verified that it is greater than or equal to 1 by pi x1 square plus x2 square. So, which is the function phi. Okay. So, for any positive definite function we can find the expression a function of class K satisfying this condition. For the theorem 1, we consider how to find a Lyapunov function. So, if we consider the system x1 dot equal to x2 and x2 dot equal to minus alpha times x1 minus beta times x2. So, if you consider this system, then 0 0 is a equilibrium point. If you equate the right hand side to 0, we get the is equilibrium point. So, at this equilibrium point, to analyze the stability, we have to find if possible a Lyapunov function. So, if we consider a Lyapunov function of this form, for example, for this, if we consider here alpha is greater than 0, beta is greater than 0. Okay. So, if we consider the Lyapunov function alpha x1 square plus x2 square, where alpha is given value in the system, then it is a positive definite function, and the v dot, that is the derivative del v by del x1, that is 2 alpha x1 into x1 dot plus 2 x2 into x2 dot. So, if we substitute from the equation, we will get 2 alpha x1, x1 dot is x2 plus 2 into x2, x2 dot we substitute alpha x1 minus beta x2. So, we see that it gets cancelled, 2 alpha x1 x2, remaining is minus 2 beta x2 square. So, here it is v dot is positive semi definite, sorry, negative semi definite. It is negative semi definite. So, this implies stability. But we can see that this system is actually asymptotic stable, because we can find some other Lyapunov function, so that it is positive definite and v dot is negative definite. So, by this particular result, we should not conclude that the system is simply stable, but if we keep trying for various types of Lyapunov function, we may conclude later that this is a given system is asymptotically stable also. Similarly, if you are not able to find a Lyapunov function, it does not mean that the system is unstable, or we cannot conclude anything about the system just because we are not able to find a Lyapunov function. So, for example, if you consider v of x1 comma x2 is a x1 square plus, let us say, a square x1 square plus b x1 x2 plus c square x2 square. So, if we take a function like this in such a way that b is greater than 2ac. So, under this condition, it is clear that similarly a is positive, c is positive. So, if you consider this, it is very clear that v of x1 x2 is always a positive value and v of 0 0 is 0. So, it is a positive definite function. Now, by differentiating this dv by dt, we will get the expression a square into 2 times x1 dot plus b x1 x2 dot plus b x1 dot x2 plus c square 2 x2 x2 dot. Now, if you substitute the values of x1 dot x2 dot from the given equation, we will get the expression to be like this. If you collect the coefficient of x1 x2, we will get 2 a square minus beta into b minus 2 c square alpha, then we will get plus b into x2 square minus b into alpha x1 square minus 2 c square beta into x2 square. So, we can see that if you select b ABC properly, then we can make this bracket to be 0. So, that is we can make minus 2a square b into beta minus 2 c square alpha. If it is 0, then x1 into x2 term will become 0, and similarly this b minus 2 c square beta, if it is strictly less than 0, then the condition will give that v dot is negative definite. So, we can easily verify that such selection is always possible. So, in this case we can conclude that the system is asymptotically stable, or the trivial solution x equal to 0 is asymptotically stable according to the theorem which we have seen in the previous lecture. So, now we will come to the following theorem on instability. So, here if you can find a function v of x which is continuously differentiable in the ball of radius rho, and v of 0 equal to 0, and it also satisfies dv by dt is positive definite in B rho. Moreover, if in every neighborhood n of the origin there exists a point x naught such that v of x naught is positive, then the trivial solution is unstable here. Okay. So, the theorem says that we consider, for example, in the case of two variable x is x1 x2 in R2, then in every neighborhood, whichever neighborhood we take, however small it is, there exists at least one point x naught, so that v of x naught is positive, the value is positive at the point x naught, and v dot is positive definite. Okay. So, in that case we conclude that the system will be unstable. So, it also implies that if v is positive definite, that is for each and every point v is positive value and v dot is also positive definite, then also it is unstable. That is a particular case. Here more general case is if at some point in every neighborhood v is positive and v dot is positive definite, then the system is unstable. So, the same theorem can be reversed. If v dot is negative definite and in every neighborhood we can find a point x naught, so that v of x naught is also negative, then the system again is unstable. So, we can also say if v is positive definite, not at some points, maybe at all the points, and v dot is also positive definite, this implies the system is unstable. And if v is negative definite, v dot is also negative definite, that is also implies unstable at the critical point x identically 0. And this is the more general statement. The theorem gives a more general statement here. So, to prove that statement, let us consider R is less than P and B R is subset of B rho. So, if you consider a ball of radius rho and a smaller ball of radius r here, and V is we have mentioned that V is a continuous function in this continuously differentiable function, therefore, it will be bounded. So, there will be a maximum value for V in the ball of radius r, okay. A maximum value is there. So, we select another number r1 strictly less than r and take a point x naught in the ball of radius r1, smaller radius r1 as a initial condition. So, for this initial condition x naught, x of t is a solution of the problem. There exists a unique solution for every initial condition. So, x of t is a solution and it is given that V dot is positive definite function, is greater than 0. Hence, V of x of t is a increasing function of t. So, this dV by dt is positive, it implies that V of x of t is a increasing function of t. So, if 0 is less than t, that is for t greater than 0, we have V of x of 0 should be less than V of x of t because of the increasing nature for all t greater than 0. Therefore, x of t cannot tend to 0 according to this result, that V of x of 0, that is V of x naught is the value of the function V at the point x naught, that is a positive value and that is less than V of x of t. That means, V of x of t is bigger than this positive value. So, as t becomes larger and larger, V of x of t cannot become 0 and but V is 0 only at the point 0, therefore, x of t cannot tend to the value 0 and therefore, the minimum value of the V dot x of t equal to m here in this case, and so we can write V dot x of t is greater than or equal to m, and integrating we get V of x of t is greater than V of x of 0 plus m into t. Integrating from 0 to t we get this expression. From this, for large value of t, the right hand side can be made to be greater than m, capital M, where capital M is the maximum value which was defined here on this ball. So, it means that this implies that x of t goes out of the neighborhood B rho here. The maximum is defined on B r, and because the value of V is exceeding the value capital M, it means that the solution x of t goes out of the neighborhood B r. It is not rho actually, so it should be corrected, it is B r. Hence, the system is unstable, that is starting from a initial condition, the solution goes out of the ball, whatever ball we are selecting of radius r, it will be going out of that one. So, the system is unstable because of the condition given here. So, here for example, we can consider the following. For example, let us consider x1 dot equal to x1 square minus x2 square and x2 dot is minus 2 x1 x2. So, this is a dynamical system. Now, it is very clear that 0 0 is the equilibrium point for this system. Now, if we define a function v x1 x2 in this form, that is 3 x1 x2 square minus x1 cube. So, let us take this function, it is given. So, using this function, or we can write it like this, x1 into 3 x2 square minus x1 square. So, we can see that this function has in a neighborhood of the origin at 0 0, if you take any neighborhood for points in this neighborhood, we can see that at some point it may be positive, at some point it may be negative. So, any neighborhood we select, we can find some point x1 x2 for which v of x1 x2 is positive or negative in any way. Now, we can easily calculate the dv by dt, v dot of x1 x2. So, that will give the value like this. If you select it, finally after substituting the values of x1 dot x2 dot in after the derivative, we will get a expression like this, 9 x1 square x2 square minus 3 x2 to the power 4 plus 3 x1 square x2 square minus 3 x1 to the power 4. So, ultimately we will get everything negative, 6 x1 square x2 square minus 3 x1 to the power 4. So, this is strictly less than 0 for all the values of x1 and x2 in a neighborhood of 0. So, this implies according to the theorem, the statement of the theorem. So, the statement of the theorem says that if in a neighborhood it is positive and v dot is also positive, the system is unstable. The reverse is, if in a neighborhood if v of x naught is negative and v dot is also negative definite, then the system is unstable. So, that is the case which we are having here. In every neighborhood we can have a negative value for v and v dot is negative definite. So, this implies 0 is unstable, x equal to 0 is unstable according to this particular theorem. So, in the next lecture we will see the stability theorem for time varying system. So far we have seen the theorems for time invariant system, and now similar theorems with some modifications are available for time varying system. So, that we will see in the next lecture. Thank you.